thank Media Services for, I mean, I just asked him last night. So luckily he's our next, the guy kind of in charge, I don't know, he's my next door neighbor. All right, let's review. So we're just talking about electricity. There's two kinds of charge, plus and minus. And as you all know, like charges repel, unlike charges attract. And now here's the strange thing that we learned yesterday. Large neutral objects are attracted to charged objects. And large is just something that has a bunch of molecules. So we'll just say like household object, okay? And that was the whole idea of polarization. So that was very non-intuitive, right? Large neutral objects are attracted to charged objects. Then we talked about the fact that charge is quantized. So if you measure the charge of any normal household thing, it's always going to be an integer times the charge of an electron. Charge is also conserved, so no matter what you do, if you measure the charge before some kind of a process and you measure the charge after some kind of a process, they're always going to be the same. And then we finally got an equation. And this is super crucial to memorize. I mean, you'll see, because we're going to use it a lot. So the electrical charge between two charged objects is this constant times the charge of one times the charge of the other divided by distance squared. So I put absolute value signs just to emphasize this only gives you the magnitude. You have to figure out the direction, you know, from this, right? You know, like charges repel, unlike charges attract. So you figure out the direction. This just gives you magnitude. And so K is this constant, 9 times 10 to the 9th, Newton meter squared over Coulomb squared. But honestly, you want to remember that K is 1 over 4 pi epsilon 0, because we're going to use that a lot later. I mean, it seems silly now, but trust me, we're going to use it. And this is supposed to be much, much greater than it. You know how it is, right? So for household objects, the electric force is tons bigger than the gravitational force. So yesterday we talked about the hydrogen atom, where the electrical force was like 10 to the 39 times as great as the gravitational force. So electric force is really, really strong. Okay, so this is a force equation, right? And what did we learn in Physics 121? That if you have more than one force, the net force, you just add them, right? That's nothing new. So here's a typical chapter 22 problem. And it's just like what you did in Physics 121. It's a force problem. All right. The figure shows an arrangement of 6 fixed charge particles. So A is 2 centimeters, and the angle is 30 degrees. All 6 particles have the same magnitude of charge, 3 microcoulombs. Remember, micro is 10 minus 6. Their electrical signs are as indicated. What is the net electrostatic force F acting on Q1 due to the other charges? Okay? All right, now in 121, when you had a force problem, what was the first thing you had to figure out or decide on? It was the most obvious thing. What was the first thing you had to kind of say, okay, that's, I don't want to give it away. You're thinking too hard. What's the object? Right? I mean, you had to figure out what's the object. And then you just, then you drew it at the origin of the coordinate system, right? Then you draw the force vectors. Okay, same thing here. Okay, so what's the object? Q1, right? Because it says, what's the force acting on Q1? So that means, because come on, you have 6 forces, 6 charges, but the one you want to draw is Q1. All right, so here you go. So here's Q1, that's the object. And now what we're going to do is just what we did in Physics 121, So, we have 1, 2, 3, 4, 5. 5 charges that are going to act or exert forces on Q1. So we just got to draw the vectors. There's nothing new here, except we're using the electrical force, Coulomb's law. Okay, so this doesn't matter the order, right? So let's do F hold on. So let's do F21. So the force that charge 2 exerts on charge 1. Okay? Okay, so Q1 is negative. Okay, so what is Q2 going to do to Q1? Okay, so what's going to be the direction of the force acting on Q1? Here's Q1, it's negative. Here's Q2. All right, so here's Q1, negative. Here's Q2, negative. So what's Q2 going to do to Q1? This way, right? Because it repels. Agree? Okay, now, this is A, this is A, this is A, this is 2A, this is 2A. Remember, Coulomb's law, F equals K Q1 Q2 over the distance squared. So, is this going to be a large force compared to this? Just magnitude? No, because this is twice as far away as this one, right? And this is a d squared. So how is this force going to be compared to that force? Just, sorry? How, by what factor?
Smaller by 2.
By 2 or by 4, right? Because it's a d squared. Okay? All right. Okay. So so there's F21. And I'm not going to give you any numbers, all right? All I'm saying is that this guy pushes this one to the right, and it's small, you know, compared to like this and this, okay? So it's small and it's to the right. All right, let's do, just for fun, let's do the force F31. So now we want to say, what does this charge, what's the force exerted by this one on our object? So what's Q3 going to do to Q1? Sorry? Okay, so what's going to be the direction of the force? Up, right? Because it's attracting. Now, how is this force magnitude going to compare with this force magnitude?
Bigger.
How much?
4 times.
Agree? 4 times, right? Because this is 2A, and this is just A. And again, it's divided by distance squared, right? So we're going to draw something up here, approximately 4 times the size as that. Agree? Okay, all right, so there's F31. Now, this one was nice because it was along the x-axis. This one is not nice because it's not along the x-axis. So in Physics 121, what did we always do with forces that were not along the x-axis or the y-axis? What do you got to do?
You could either rotate the axis.
Okay, we're not going to rotate the axis.
To break it up into X and Y.
Yeah, you got to break it up into components, right? I mean, you have to. Okay, so you just do it, right? So this one is cosine, agree, because it's adjacent. This one is sine because it's opposite. All right? So any questions? Okay. All right, now let's just do the others. So let's see, we did 2, we did 3. What's this one going to do? So what's going to be the direction of the force? Down. Agree? Now, how's this magnitude going to compare with this magnitude? Same. So we're going to have it going there, right? What's this one going to do? Attract. Strong or weak? Strong. What's this one going to do? Strong or weak? Weak. Okay, so there you go. All right? So let's see. So this one attracts, this one repels, this magnitude is the same as that magnitude. This one is strong. Let's see, what else? I'm sorry, yeah. Okay, so look at that. That's not right. So just guess what the answer is going to be. Our favorite number. Huh? 0. Yeah. All right. So all I'm saying is, come on. This is 121, right? It's just a regular force diagram problem. The only thing is you're using Coulomb's law. So big deal. In 121, you know, we had tension, we had gravity, you know, all these things, but now we're just using this new force law. Okay, so there's nothing new. But you know there's going to be a problem like this for homework, and I'm probably on a test, because you have to get a Coulomb's law problem, right? Because Coulomb's law is super, super incredible with electricity. Okay? All right, there you go. Okay, now let's get to the fun stuff. We want to talk about force fields, specifically electric fields. We'll do magnetic fields the second half of the semester. Okay, force fields. So here's your history lesson. So around 1830, there was a guy named Faraday. You're going to hear a lot about Faraday. He invented this concept of a force field. Now, you know how lazy physicists are, right? So we don't usually call it a force field, we just call it a field, okay? So just remember, if I say a field, I mean a force field. So he invented this idea of a force field in order to visualize electric and magnetic forces. So here's the motivation. So, okay, we're talking about electricity, but it's easier to show pictures with magnetism, but it's the same idea, so don't worry. Okay, so let's say I have a piece of iron with a knife or something that I don't like. If I just chip off a piece of, you know, I keep chipping off pieces of iron, you get these iron filings. So let's just say I had a whole bunch of iron filings, and then I put a magnet down. That's what it's going to look like. That's what's going to happen. Okay? So, you know, what's going on? I mean, it looks like, you know, I mean, these things are not touching the magnet, right? So it looks like something's happening to the space around the magnet. Agree? Something's happening to the space around the magnet. Okay, here's another one. This is just a close-up. And another one, okay? All right. So something is happening to the space around the magnet. And Faraday came up with this idea of a force field just to kind of help him discuss this or understand it, okay? So here's the definition of a field. So this is the mathematical definition of a field, okay? So a field describes a function that assigns a value to every point in space. Thanks a lot! You know? Well, you think that's bad. Wait until I show you the physics definition. Okay, here's the physics definition. It actually makes sense, but you get to read it like 3 times and think about it. All right, so physics, we say a force field is the effect that a source of the field, like a charged particle, has on the surrounding space. All right, it's an effect that something has on the surrounding space. Now, it's not an effect on the things in space, it's an effect on space. That's important, okay? All right, so here, since a field exists in empty space, a field is a property of space. It's a stress or an alteration of space. Are you guys confused? A little? You should be, because it's weird, right? So that's what we're going to talk about right now, okay? All right, yeah, I have written in my notes, clear as mud, you know? Okay, so here's how it works. So let's say we have an electric charge, okay, a positive electric charge. So here's the important thing. A charge, anything that's charged, creates an electric field, okay? That's what's going on here. So we have this positive charge, and it creates an electric field. And so for an electric field, we just call it an E field. It's nice, right? E, electricity. Guess what it is for magnetism? B. Yeah, I know. Because M is always mass. But don't worry about it. All right, so for electricity, E field. For magnetism, it's going to be a B field. But we'll get to that later. All right, now here's the thing. You have this charge, it creates this E field, and the E field propagates throughout space, all right? It propagates throughout space, so it exists everywhere, okay? It exists everywhere. Now, okay, here's the deal. So here we have this positive charge, creates this E field. E field propagates throughout space. Now let's just say we put another charge here, what would this charge feel? And I'm being really careful with my words. What would the second charge feel? Come on, you have a positive charge here and a positive charge here. What would it feel? Well, just one word, starts with an F.
Force.
Force. Agree? Right? So this guy would feel a force, okay? So here's the key. Fields are associated with forces. I'm making a big deal out of this for a reason, which we won't learn until 3 chapters, okay? So whenever you think of fields, you think of forces, all right? Fields are associated with forces, okay? Fields and forces, F squared, fields, forces. Walk around campus saying F squared, fields and forces. All right? Now, okay, so, we know that this guy's going to feel a force. It's going to be repulsive force, right? And we know all that. But what we kind of want to discuss is what's going to be the magnitude. What's going to be the magnitude of the force that guy feels. Okay? All right? So we got to have something to measure the force, okay? So what we typically do, we want this to be really, really small. What is small? Small enough. What does that mean? We don't want this to disturb this, okay? So this is like, in calculus, epsilon and all that stuff, epsilon approaches 0, right? So this is just this tiny, tiny probe charge. It's small enough not to have a big effect on this, okay? So the probe charge, we're going to use that to measure the force, okay? So this is what I'm saying. If this guy feels a strong, strong force, what does it mean for this? Big charge or little charge? Big. If this guy feels a tiny, tiny force, what does it mean for this guy? Okay, now let me ask it a different way. If this guy feels a huge force, what does it mean for the E field? Big or small? Big. If this guy feels a tiny force, what does it mean for the E field? Small. That'll make sense. Just hang on, okay? Hang on. All right, so the probe charge is going to allow us to determine the strength of the E field, which is caused by the source charge, okay? Let's talk about gravity. Okay, so so we have a charged particle creates an E field. What do you think something with mass, what kind of field is that going to create? With mass. This is a 121 question, although we didn't talk about it. Okay, then think about it. A charged object creates an E field. So something with mass, what force is associated with mass? Gravity. Yeah, so therefore a massive object is going to create what kind of a field? Gravitational field, right? We didn't talk about that in 121, but it's true, okay? Electric charges create E fields. Massive objects create gravitational fields. Okay? All right, so let's say, here's a massive object, and here's another object. What is this? This thing creates a gravitational field. When this thing is in the vicinity of this gravitational field, what's it going to feel? Gravity. Gravitational force, right? Because fields are associated with forces. Okay? You're getting it? All right. Here's the Earth. Nice picture, huh? Okay, so the Earth creates a gravitational field. The field propagates out through space. All right? Now, so the field is everywhere, okay, surrounding the Earth. Now, if I'm out here with my little rocket ship, what am I going to feel? Okay, say the F word. Force! Right? I'm going to feel a gravitational force. Okay? Because fields are always associated with forces. Okay? Awesome. All right, here's a good question for you. And you can't talk to each other. You got to do it by yourself. Here's a hint. Fields are, well, no, I guess that's probably going to get you confused. Forget it. Just think from what you've learned so far. So there's only one proton. So you have to remember Physics 121 too, you know? So there's one proton. One proton. One object. Okay, you ready? Ready? Let's vote. Yeah. Okay. How come there's not an electric force? Yeah. Remember, a force is an interaction between two or more objects, right? If you have just one object, you can't have a force. Okay? So you have this proton that creates an electric field, and that's it. Now, how come there's not a magnetic field? Because we don't even know what that is yet. All right, so don't worry about it. Okay? We don't know about magnetism yet. Okay? So you have a proton, it creates an electric field. There's no other objects, so there's no force. If there were another object, the other object would feel a force, right? But there's no other objects. Okay. All right. So here's a piece of glass, a glass rod, which is an insulator, yeah? So we're going to take a piece of silk or something like that, and we're going to rub it. And when you do that, the glass actually loses electrons. All right, so it becomes positively charged. Ta-da! So it's positively charged, so what does it create? What do the positive charges create? An E field, right? An E field, which propagates out through space. But I couldn't show all the arrows, you know, because it's kind of hard on a two-dimensional screen, right? Okay. So E field is created. Now, let's say I put a little positive charge nearby. What's it going to feel? Force. Am I being repetitive or what?
It's okay.
Well, there's a reason. All right, now here's the question. All right, here's the question. When will this particle feel the force? So in other words, you know, I'm going to rub this glass with my silk. There's going to be an E field created, and then I'm going to stick this here. When is it going to feel the force? Instantaneously, or is it going to be a little bit of a time delay?
I'll go for time.
I mean, we've never talked about things like that before, right? I've never asked you a question like that. Okay, here's a similar question. It might not seem similar, but it is. Let's say that the sun were to suddenly explode. Okay? How long would it take us on Earth to feel the gravitational effects? Would it be instantaneous, or would it be a delay?
Delay.
Now, you know, look. So here's Newton's law of gravity, right? Does Newton's law of gravity have any time in it? No. So according to Isaac Newton, if the sun were to suddenly explode, how long would it take us to feel the effects? Instantaneously. Okay? Now, does that make a bit of sense? The sun is 93 million miles away. 1.5 times 10 to the 11th meters. Does it make sense that we would feel the gravitational effects instantaneously? 93 million miles away?
Yes.
Okay, here's another thing to consider. So Einstein showed, somebody already said it, Einstein showed that nothing can travel faster than the speed of light. How long does it take light to travel from the sun to the earth? 8.3 minutes. All right? So nothing can travel faster than the speed of light. It takes light 8.3 minutes to get here. So if the sun were to suddenly explode, Does it make a bit of sense for us to feel the gravitational effects instantaneously? No, not at all. Okay? All right. So there is a delay. And I'm going to just tell you, but we're going to discuss this in gory detail later on. Sorry. All right? So the answer is that these force fields, gravitational force fields, electric force fields, magnetic force fields, they travel at the speed of light. Okay? So in other words, if this thing were charged, and then I suddenly stuck this thing here, you know, it's going to take the field not very long, right? But it's not going to be instantaneous, you know? It's just going to be a slight delay. Super short, because it's traveling at the speed of light, right? But there's going to be a delay, okay? And that's actually important. All right, so this is what we have to work with. Okay, so here's Newton's model, which is wrong. It disagrees with relativity. So Newton's model says this. So Newton's model is called the action at a distance. It just says that Q1, let's say we have a Q1 here and a Q2 there, all right? So Newton says Q1 and Q2, they interact instantaneously. It doesn't matter if Q1 is here and Q2 is at the other side of the universe. They interact instantaneously. It's wrong. Einstein, so here's Faraday's field model, which agrees with Einstein. And it sounds like we're making a mountain out of a molehill, I agree, but you have to because it agrees with experiment, you know? This disagrees with experiment. So here's the field model. The field model says Q1 creates an E field E1, propagates throughout space at the speed of light. Q2 creates E2, propagates throughout the space at the speed of light. It's the fields that interact, all right? I mean, it sounds like mountain out of a molehill, don't you think? But it's how it works, okay? So this actually agrees with relativity, so everybody loves it. So that's why we're going to be talking mostly about fields in this semester, E fields and B fields, because you have to, because, I mean, it works. Okay, now, okay, good. Let's go back. So here's this positive charge. It creates an E field. E field, okay, it goes out throughout space. Now notice, so this represents the magnitude. Okay, so if you're this far away, small magnitude. If you're this far away, big magnitude. So the E field depends on the distance, okay? But it also has a direction, right? It's away from the plus. So an E field, what kind of a field is it? Is it a scalar field or a vector field? It's a vector field, which is going to cause us a lot of trouble. Mathematically, that is, okay? But that's life. What are you going to do with it, right? Okay, so these lines, they're called E field lines. You know, they don't exist. I mean, there's nothing there, but they just give you a visual of the strength and the direction of the E field. We're going to have a lab on E field lines pretty soon, right? E field lines. Not for a while, but okay, E field lines. Okay, now, so another history lesson. In the 1860s, another famous guy called Maxwell. So in the 1800s, lots of people, in the 1700s and whatever, a lot of people had been doing experiments on electricity and magnetism, but nobody had written a mathematical theory. And it's incredibly important to have the theory, because then you can use it to predict new things, you know? All right, so this one guy, James Clerk Maxwell from Scotland, he said, I think I'm going to go write a theory about electricity and magnetism. He was very bright. So he did it, all right? So he took everything they knew at the time, and he wrote a mathematical theory. 20 equations. 20 equations! Luckily, there were some other brilliant people who realized that you could combine them. So they spent like 20 years, or I don't remember. They spent like 20 years combining the 20 equations into 4. So guess what Physics 220 is about? The 4. I mean, seriously. I mean, there's a lot to it. Oh no, no.
Equations like.
Oh no, there they are. Now, these projectors, I don't know what the deal is, but this here, it's supposed to be this. And have you ever seen that before?
Yeah.
You have?
I don't know what it means. I'm saying I don't know what it means.
Oh, well, we're going to learn it. Don't worry. Okay, now here's the important thing. So these 4 equations explain everything there is to know about classical electricity. Oh, don't write them down. It's not worth it. I mean, these 4 equations explain everything there is to know about classical electricity and magnetism. Everything. And here's the important thing. These equations are in terms of fields. E field, B field, E field, there's a B field in there. B field, there's a E field in there. All right? So fields are fundamental. You have to understand fields in order to understand electricity and magnetism. Okay? And you will, don't worry. I know it sounds sort of la-la landish right now, but don't worry. Okay.
Magnetism, right?
Sorry?
Means magnetism.
Yeah. Some books actually use H. So, uppercase H. Most people use uppercase B, so be grateful, right? All right. Now what we want to do is we want to define E. Okay? We want to define E. So now I want everybody to pinch yourself to make sure you're totally awake, because you really got to pay attention. Okay, so everybody totally awake, because we're going to define E. All right? All right. So here's a dead fish, and it's been outside in the sun for a very long time. It hasn't disintegrated yet, but it's been outside for a while. So, what is the dead fish's most obvious and unpleasant property? It smells. It stinks. Agree? All right, it stinks. Okay. How would you measure the strength of the dead fish's stink? What would you use? Your nose. Agree? Your nose, because we don't have any instruments, right? You're going to use your nose. Okay. Does the nose have anything to do with the source of the stink? No. What's the source of the stink? The fish. Okay, everybody agree? The nose is just used to measure the smell. All right? Okay, very good. Here's a positive charge. What does it produce?
A field.
An E field. And the E field lines are shown, right? These E field lines are shown, right? So this is strong E field, points this way. Small E field points that way, so forth and so on. So the E field lines are shown. Okay. How can we measure the strength of the E field? What do we need to measure the strength of the E field?
Our noses.
Sorry?
Our noses.
Okay, we need something like a nose, right? What's it going to be?
Something.
What's it going to be?
I don't know.
Come on, you do too. Okay, remember, what are fields associated with?
Forces.
Forces. So if we want to measure the strength of the field, we want to measure the strength of the force. And what are we going to use to measure the force?
Something.
Like a charged object.
Oh.
Right? Now, we don't want to disturb this, right? So what kind of a charged object are we going to use? Super small. So a probe. Okay, it's just a charge, but we call it a probe because it's probing, you know? All right? Okay. Now, does the probe charge have anything to do with the E field created by this guy? No, it's just like the nose, right? We're just going to use it to measure the force. Agree? Okay, everybody with me so far? All right. So this is how we're going to define the E field. This is a big deal. So the E field is defined as the force between the charge that created the E field and the probe. But that force depends on the probe, right? And we don't want the E field to depend on the probe. So what are we going to do? We're going to divide by the probe. If we divide by the probe, this only has to do with the E field created by the charge. Now that's important. That's kind of a big deal. So you want to think about that, okay? So again, the force depends on both charges. So if we divide by the probe, this only depends on the charge that created the initial E field. Okay? So the probe is like the nose. Are you with me? All right. Okay. So let's do the easiest example possible, yeah? All right. Let's do the easiest example possible. Okay, so what we want to do, and we're going to use this forever, so what we want to do is we want to calculate the electric field for a single charge, okay? So we always call this a point charge, because we don't want to, it just makes it easy, right? So we're going to call this a point charge, okay? We don't want to deal with the size or anything like that, just a point charge, okay? So you ready? All right, so here it is. Okay, so the E field of a point charge. All right, so here's the definition. The E field is the force divided by the probe. Agree? Okay, so they don't always, but sometimes they put this little prime thing here, right, just to kind of emphasize it's a probe. It's just a charge, though, All right, so according to Mr. Coulomb, what's the force between these two objects? What do I write?
That equation thing.
Okay. K. I'll just put up, I'll just put Q. K, Q, what else?
The other one.
K divided by distance squared. Yeah, sometimes I use R, sometimes I use D, all right? And then what do we have to divide by? The probe, right? Okay, so then what does this become? How come Kate is the only one speaking? Come on, you guys, you gotta participate. All right? Now, so that's the E field of a point charge. You notice it dies off as 1 over R squared, which kind of makes sense, right? So this one's really close, it's big. This one's further away, it's small. Again, it goes as 1 over R squared, okay? So if you double the distance, the force is 1/4, Now, this is, this is not right, sorry. Get rid of these vector signs. I'm just doing magnitude, so no vector signs, okay? Now, the direction is away, right? 3 dimensions, away. So how do you do that? So this is how we do it. So this is called, remember we had I hat, J hat, and K hat in 121? Well, this is R hat. It's the radial unit vector. It just points away. All right, so just imagine 3 dimensions. It just points away in 3 dimensions, and its magnitude is 1. Okay, so this is the proper way of doing it. The E field of a point charge is KQ over R squared times R hat, where R hat is away. Okay, there you go. Now, what if we had more than one point charge? What would we do then? Add them. Yeah, okay. All right. Add them. By the way, this is for a positive, right? This is for a positive. What do you suppose it would look like if this were a negative charge? How would the arrows be directed? In. You want to remember that.
So they are?
Oh yeah, it's the same thing, it's just that they point in. So just like it would look like this. All right, that's all. Okay? All right.
Are we just assuming those particles are positive?
Sorry?
Are we just assuming those are positive?
Oh no, I told you it was positive. Yeah, you don't assume. Okay, all right, everybody happy? Okay, now we're going to look at, now we're going to do it just a little bit differently. All right, so there's our, you want to memorize that. Even if you don't want to, you will, because we're going to use it all the time, but you really want to memorize it. Just KQ over R squared. KQ over R squared, all right? KQ over R squared. All right, now let's look at this a different way, because we want to get a different equation. All right? All right. So, here we have, this is supposed to be a vacuum. Does it look like a vacuum? Vacuum, right? But then we stick this charge here. Okay? So we stick a charge in a vacuum. Okay? Now what we're going to do is somehow we're going to create an E field. How'd you like that? Pretty good, huh? All right? So we had a vacuum with this poor little charge here, and then we create an E field. Okay? Now, what is this? What's the force that this guy is going to feel? All right, hold on. Okay, what is it? So what is it? So what's the force? What's the force that this little guy feels from this big guy? Come on, Coulomb's law. Yeah. Is that what you said? Now you didn't hear you or something?
No, I didn't say that.
Oh, so the force is K, big Q, little q, divided by the distance squared, right? I mean, everybody agree? Okay, now, just watch what I do. That's equal to K, Q over distance squared. See, I'm being inconsistent, right? I had R the last time, now I have D. Who cares? Same thing, all right? Okay, so is that the same as that? Did I cheat? No, I just put, big deal, right? I mean, that's good math. Now, what is inside the parentheses? What's that?
That's the E.
E! So there. Is that correct? Is that correct? Yeah. So here's another equation that's incredibly important. But you got to be careful, I mean, look, I defined the E field like this, right? That's how I defined the E field, agree? So, right? The force divided by the probe. So you can just look at that and say, well, mathematically, F equals QE, right? I mean, right? But look at it, it's a different concept. This is the definition of an E field. This is how you have to interpret this. If you have an E field and you put a Q in it, that's the force it's going to feel. Okay? So mathematically it's the same equation, but the concepts are completely different. Right? So, you remember that. Okay, so this is a big deal. So I guess there's two equations I want you to I really want you to memorize them. Usually we don't have to memorize things, right? Because I give you all the equations, but we're just going to use this so often. So in my opinion, you want to memorize Coulomb's law for sure. Okay, I just lied. 3 equations. All right, so memorize Coulomb's law. Memorize this. Notice this is a vector, this is not a vector. And memorize this. All right? I mean, it's just going to make life easy for you later on. All right. So that's all the theory we're going to do in this chapter. Now we're going to do a bunch of problems, but we're out of time. So Monday, so really review this stuff. Make sure you remember these 3 equations. And then Monday, we're going to do a bunch of problems. It's going to seem just like 121 again. So, thank you very much.
Thank you.